All right, quick introduction. So I'm Lewis. I'm CTO at Dataform. Previously, I was an engineering manager at Google. Before that, software engineer. I worked in ads. Apologies. So, fun fact: there's no data engineers at Google. That's not like a role that we had, or had when I was there at least. I guess this is partly because everybody pretty much who built software at Google was working with data. The teams and projects I worked on were generally just massive data processing pipelines. We used stuff that internally turned into things like Apache Beam, mostly wrote Java. I think there's some shifts have changed in the industry since then, and we're going to talk a bit about that, talk about SQL, talk about some of its problems. So my plan is to go through the following. First off, I want to kind of introduce you to our kind of reference architecture, the architecture that we kind of generally propose for building out your data stack if you're revisiting it or if you're starting from scratch. Then talk a bit about why we do love SQL for data transformation, some of its benefits, why we don't love SQL for data transformation, some of the problems that it has, and then talking about how we can fix those problems with concepts from metaprogramming and compilers, and then finally kind of talk a bit through the open source framework that we developed for helping you do this. Maybe I'm jumping to the end. This is basically the answer to my question. This is why we did it. We want a scalable solution for managing data transformation processes that works for data engineers, data analysts, data scientists. So how do we get there? All right, let me introduce the reference architecture. So you can build a data stack in many different ways. I'm sure many of you have something that looks different to this. Maybe some of you have something that looks similar to this. We're seeing a big rise in data warehouses. They kind of really changed the game, given their ability to scale to petabytes of data with a very simple to use interface being SQL. Things like BigQuery, Snowflake, and Redshift are all extremely scalable SQL-based data warehouses. Maybe Redshift is less scalable than the other two, but the kind of concepts that enable them are the same. So we generally advise when we work with customers looking to build out a data stack, an architecture like this, where you use an ELT model instead of an ETL model to move raw data into your data warehouse. Once it's in there, you transform it, you model it, you create new data sets that you then feed into your BI tools, reporting, dashboards, machine learning projects. It's a lot simpler to manage. It does have some drawbacks. Ultimately, what we're trying to do here is build a kind of single consistent view for data across your entire company. And that's really that kind of data modeling process and where we think so much time is actually spent. OK, so SQL. If we're using a data warehouse, we're going to be using SQL to do those transformations. We like it because it's a common language for data definitions that a wide range of people can understand. Product managers, data analysts, data scientists. SQL's relatively easy to get to grips with. Modern warehouses scale extremely well. Particularly BigQuery and Snowflake really can handle petabyte scale, which is incredible, without having to manage any infrastructure whatsoever. It's easy to iterate and develop. We can send a new query to our warehouse, and in a few seconds, we can work out if it's going to run. Maybe we actually get some results back. And it's relatively easy to debug as well. We're not actually having to deal with code or deployment or building containers, managing infrastructure. But there are some drawbacks. It's hard to adopt software engineering best practices, things that if you are a data engineer or software engineer, you would be familiar with. How do you release new versions of SQL pipelines? How do you version control all of that information? How do you do things like unit testing? How do you reuse code between different parts of your data stack? These are all things with pure SQL are quite hard to accomplish. One of the main reasons for this is SQL is not a real programming language, really. There's no control flow. There's no iteration, recursion. It's a fully declarative and static language, and that makes it hard to do some of the things we just looked at. There are some exceptions to this, like T-SQL, if you've worked with SQL Server, allow you to actually do some of this stuff. I'd argue you probably don't want to do that. There are better ways to accomplish these things, which we'll go through in a second. OK, so metaprogramming. This is a fairly broad kind of set of tools that we can use to address some of these issues. But to kind of summarize what we just talked through, there's a number of reasons why we love SQL. There are a number of reasons why we don't really want to run our production data stack on it. And we need to find a way to fix those problems. OK, so metaprogramming, a technique in which computer programs can treat other programs as their data. This is all from Wikipedia, I'll admit. But this one is the second piece is particularly relevant because it's what we're going to do to solve some of these problems with SQL. We want to use metaprogramming to introduce a compilation step for our SQL, which allows us to move some of those more interesting computations, such as for loops, iteration, recursion, reusable code, into a kind of compile time step. In this sense, we're kind of treating the SQL queries or programs as our data, which is why metaprogramming kind of applies here. So one of the core problems with SQL is that you don't really have parameterizable functions. When you write a SQL query, it's really just like you can think of it like a block of code. It's not in a function. We can't put parameters in. We can't change its behavior or change the input or change the output. This is really the fundamental problem, and fixing this actually gives us a lot of other things kind of automatically. So we want a way to be able to write iterative code or imperative code, recursive code. We need some basic control flow. You can't do many interesting things if you don't have at least if statements. The way we'll ultimately end up doing this is through data flow graphs. I imagine everybody in this room is familiar with a data flow graph, whether you've used a tool like Airflow or God knows what else. Pretty much every kind of data processing system is some kind of data flow graph with dependencies, which provide a simplified model for us to describe how the data flows through our system. So by doing all of these, we can actually use SQL as our primary way to transform our data. But we can do it in a way that actually scales. We can version control the stuff. We can support things like environments, release processes, and testing. OK, so jumping ahead a little bit, we've been developing an open source framework to address some of these problems over the last few years. It's called Dataform. It's a TypeScript framework that we've written in TypeScript anyway. It supports BigQuery, Redshift, Postgres, Azure SQL data warehouses, and it provides a number of abstractions on top of SQL. It's at its core a compiler. I'll kind of justify why we think of it like that in a minute. So it has a few different components. We have a data flow format, a way to define actions and dependencies between those actions and visualize how the data flows through our system. We have introduced a new language for SQL called SQLX, which allows us to actually introduce kind of traditional programming concepts and write for loops, parameters, so on. We have a compiler, a compilation process, which we'll dig into in a second. And then a number of abstractions inside the framework, which aren't really kind of metaprogramming itself. They are just part of the framework for common SQL tasks like documenting data sets, writing assertions, writing unit tests. So this is what we're trying to do. Parameterize SQL, Think of our SQL code like functions, enable code reuse. The number of SQL queries I've seen in projects I've worked on before where somebody simply takes a massive 200-line query, copies it, and changes a few things is crazy. We shouldn't be doing that. If we were building software, we would never do this. We fundamentally need this data flow graph, these directed acyclic graphs, and then a few other things that I mentioned. So assertions, unit tests, documentation, environments, staging, production, release processes. OK, so this is coming back to the metaprogramming piece. We think of Dataform as a compiler. We have a number of files on disk. Those are a combination of SQLX files, maybe plain SQL files, maybe JavaScript files, where you can do pretty much anything you want and interact with the open source API to define actions in this graph. You can write imperative code at this point. You can write for loops. We'll see some examples of that in a minute. This is sandboxed. And after compilation, we turn all of these files on disk. And you can think of this like Webpack or even C++ compiler, say. We turn this into some kind of runtime format for our SQL program, which is a data flow graph. And we call this the compile graph. At this point, we've taken all of this imperative code that we've written, and we've turned it into pure SQL. This is just basically a big JSON object. We have a final step as well. We call it build. Maybe it's not really build, but this is how you often label these things in software, which is where we take the compile graph and we actually combine it with information from our data warehouse to work out the actual final SQL statements that we want to execute. OK, so I mentioned we're building this graph, and we think about actions inside that graph, and there are a few that we kind of support at the moment. The primary thing that our users do and that we do on our own projects is publish new data sets. I've written a SQL query. I've combined some things together, and I want to publish a new data set to make it available to everybody in my company and push it back to the warehouse. This is the main thing that we do. You can also write custom SQL scripts. Maybe you want to go and delete some rows from some tables. Data assertions, we'll dig into those in a minute. But they allow us to test certain things about the quality of our data, make sure there are no null values, or enforcing primary keys, which is something that you don't really have native support for in most data warehouses. Unit tests and external declarations is another part. I mentioned the data flow graph. This is a simple example from one of our demo projects. Again, I'm sure you've seen stuff like this before, and it's very familiar to you. Each of these squares being some kind of action. In this example, I think they are all kind of publish actions. And this maybe gives you an idea of how we see the typical kind of data modeling process happening. We have some source data sets, data coming from third-party APIs, for example, Stripe. Data coming from Shopify, maybe our CMS. We combine these to build statistics about orders. We combine information from our CRM about our customers to build up kind of final tables like daily revenue stats, things that we would use at that final layer for our reporting and BI. OK, so this is a code sample. This is a plain vanilla SQL query, which creates a new table. Given that that's the primary thing that we're talking about doing with Dataform, this is what it would look like. We want to create a new table. We give it a name. We add a select statement, and we're done. The problems here are we can't really parameterize any of the settings here. So we can't write like a test for this. We couldn't parameterize settings such as the size of the age bucket in this simple like group the count of users by an age bucket. So this is kind of an introduction to the SQLX format. Instead of having to write pure SQL, we expose some kind of APIs in a way to tell the Dataform framework how to treat the SQL query. So there's a difference here in that we're not writing a create table statement anymore. We're just writing a select statement, and that's how we think about, if we want to publish a new table, we're not thinking about writing a create table statement, we're thinking about writing a select statement to generate that data set. There's a config block at the top. This is part of the SQLX format, which tells Dataform what kind of table we want to create, whether it's a table or that could be a view, and there's a few other modes as well. So all of this boilerplate is abstracted away. This is particularly relevant for certain warehouses where you can't actually do this reliably or repeatably. If you need to create temporary tables and swap them in once they've finished loading to minimize kind of downtime, all of that stuff is abstracted away by the framework and by the compiler, so you don't really have to think about it. We have a couple of other pieces in this script on the right, different from the vanilla SQL. We're actually referencing some external variable for our age bucketing, so we could, in theory, control this kind of parameter across a number of different SQL queries. And the most interesting one is at the bottom is we're using a function called ref, which is a built-in function. This is actually what enables Dataform to build up that dependency graph of all of the actions in the kind of previous step. So we never have to actually declare these connections directly. We don't have to write all that out. As we write our SQL query, as long as we use these constructs, Dataform kind of infers the shape of the graph and the dependencies between different data sets. So this is what we had before, and this is what we have now. And when we compile it, this is what we get. So this is just one portion of the compiled graph. As I mentioned, it's just a big blob of JSON. Technically, it's a protocol buffer, but that doesn't really matter. We have a lot of metadata in here about what we're trying to do. So I think there's a mismatch here, but this is saying that we want to create a view in our data warehouse. The schema is defined. We didn't actually define that in our query. That was a project level setting. We extract the name, and we turn our SQLX contents into an actual pure SQL function. OK, so once we've compiled it, we still don't have any create table statements. Dataform's not going to do anything when we run this. It's just a description of what you want to happen. This is the execution graph, which happens after we build. And as I mentioned, some information is pulled from your data warehouse to generate this. But at this point, we actually remove some more of that data, metadata, integrate it into the query, and generate a create or replace view statement. And we're maintaining the information about the interdependencies across the project. So this is an open source framework. You can do this. You can create those files. You can compile it. You can run it. This isn't from those examples. This is our actual project, where I think we have like 56 different data sets or actions that we're performing. You can compile those, and you can run those, and they will run in the correct order, and they will be generated inside your data warehouse. Cool. So to summarize, we can write any code we want during the compilation phase through SQLX or JavaScript files. But the key feature that we kind of kept is that after compilation, we have a representation that is pure SQL, well, SQL inside JSON. Everything in there could just be run as a query. There's no user code running at runtime. And this kind of massively reduces possible bugs or infinite loops or things that you really don't want to happen. And it means we can kind of validate and verify that your project isn't going to just run forever, for example, once you actually tell it to run. And this is very much why we think of it like a compiler. Cool, so a short note on reproducibility. We want to make sure that a given Dataform project, when compiled, as long as none of the inputs have changed, it will produce the same output. Most kind of language compilers are good at doing this. Because you can actually write real code inside Dataform, you do have to be a little bit careful. And this is kind of more of a best practice. We actually sandbox compilation so that you can't read from a network or read from files on disk, and that kind of helps improve that reproducibility while restricting you in a few ways. If you use things like math.random in your compilation code, then you're going to end up with a non-reproducible compilation step. I don't think anyone's done that yet that I'm aware of. OK, so I have a few examples, kind of real use cases of maybe things that you wouldn't have really thought about doing or would have seemed hard to do with SQL kind of on the surface, but by introducing this framework, by allowing us to write imperative code, we can actually do these things. So obviously, everybody knows about GDPR. You have the right to be forgotten, but we're all there writing SQL, creating new tables, and filling them with information about our users and PII. If the user asks to be deleted, we should probably go and clean all of those up. This is a script which takes a list of tables which contain PII, and are derived from kind of some original source tables. And for each one, we'll generate a GDPR cleanup script, which will delete all of the rows in the table where the user ID is in that GDPR deletion request table. I've just put 3 tables in here as an example, but one of our users, I think, has about 50 different tables, which are all kind of downstream produced tables from their original source tables. If they had to write this SQL query and manage it for each one, that would be a nightmare. And this is kind of the first example of somewhere where actually allowing us to manipulate SQL in a programmatic way can really reduce the amount of code that we have to maintain. So this is a slightly more interesting example. You probably never thought you could write a unit test for a SQL function, but you can. And here's a kind of example of that. So we have 2 things here. We have a function or a Lambda function which takes a few parameters. We have our parameterized SQL now to generate that query that we saw in the original example. This means the nice thing about this is we can change the input. And if you want to write a unit test, you need to change the input to your function. Because we've parameterized it in this way, we can. We could publish our users by age table in the same way we did in the previous example by just invoking this function, passing it in a table reference, and our 5 bucket parameter. But because we've written this in this way, we can also actually write a unit test where instead of telling it to point at a source table, we can provide it with some mock sample data as input. We can tell it what we expect as output, just as select queries, and we can run this as a kind of self-contained unit test. So if you have extremely complex SQL logic, which your whole data pipeline depends on, you can actually pull that out and consider writing a unit test for it. Here's another example kind of related to releases. So in software, again, you're typically going to have staging and production environments. You're not going to just push your code to production the moment you finish. You're going to push it to staging, and you're going to wait to make sure everything works as intended. In data pipelines, that can be tough, because sometimes that production data pipeline might take 12 hours to run. So this is kind of, again, a real use case where we actually wrap up we parameterize our function, and we set a sampling rate for our data only when we're in the staging environment. So our staging environment will run a complete copy of our data pipeline, but it will only be running on 10% or even less, 1% of our data. This is definitely, don't do this. I just talked about how that was bad. You could write this in a deterministic way, like a way that would mean that each time your staging pipeline runs, it does actually do the same thing. But this is just this is like math at random. OK, and then final example to kind of, which maybe shows off a slightly different aspect of being able to do this, of what you can do with Dataform. So there are certain things, common use cases that we have. If you use Redshift, maybe you're loading and unloading data from S3. And actually, in order to do that, you have to write a ton of SQL statements in the right order, sequence of operations, which can be kind of tricky to get right, or maybe you have standards that you want to enforce across the company. We can wrap this up in a function and then have our users call that with a kind of consistent interface. So rather than writing the raw SQL, I've put this example in, and I'll share a repo at the end which has these code examples where we have a kind of nice simplified interface for loading data from S3, and it does some automatic things like loading the data into a temporary table, and only once it's loaded, swapping it out, renaming it with the table that we actually want to create. So these kind of complex tasks can be repeated and reused without us having to just write tons and tons of very similar looking SQL. To give you an example, this generates maybe some SQL which looks something like this on the right, which is the original way of doing this. Cool. OK, so that is Dataform, the compiler, the framework. That's all open source, and I'll share a link to the end. Final little piece on what else we're building. So I think one of the biggest challenges we saw with frameworks like this is they're complex. Like explaining this to someone is a kind of big jump. Developing this kind of stuff using just the open source framework or command line can get pretty confusing. So what good is a new language without a IDE? And I'd say actually we've put a tremendous amount of our energy, along with the open source framework, into developing this web-based IDE for Dataform projects to make it easier to develop and understand what's going on, write SQL, see how it's compiled in real time. I think one of the reasons for this is data analysts or people working with SQL, one of the things they love about it is that development speed. So it's very easy to start writing a query, check it, preview the results, wait till you're happy, maybe write a test now, and then save that. And we wanted that process to be just as smooth writing Dataform SQL language as it is writing pure SQL. So it's an IDE for Dataform projects. It compiles and validates your SQL in real time, integrates with Git, and also manages some of the continuous integration, continuous deployment, like release processes that we kind of talked about. There's also some kind of standard stuff that I guess you would expect from any data platform, which is orchestration, scheduling, run logs, notifications, and the data catalog, which is a bit more interesting. So to give you an idea, this is what it looks like. It looks a bit like an IDE. It's fully web-based. We write our Dataform SQL in here. And it's a web-based editor based on VS Code. And on the right, we get a compiled query. We can see the pure SQL as a result of this compilation process. We can preview the results. We can publish this table. We can actually see if our query validates against BigQuery. Is the resulting SQL actually valid SQL? Similar to how like most SQL IDEs do. And then we have kind of Git controls on the top, so you can actually make a change and push it without having to really go near a command line. Talked about that data flow graph. This is a real one. This is our project again. This is at least part of our actual Dataform project, and some of the modeling that we do. So it becomes really easy for us to build up this very complex graph very quickly without really having to write any code. And we can kind of explore and understand how different parts of our data stack depend on each other. And then finally, I mentioned the data catalog. So as your data schema starts becoming increasingly complex, we'd highly recommend that you try and document some of those data sets and explain what this table represents, what the columns in that table represent. If you want to build a consistent view of data across your company, it's really important to have this metadata. Otherwise, someone's going to come along, write the wrong query, or misunderstand what that data represents. So documentation is part of the whole framework and part of the IDE. And you can see an example here where we're describing the table and describing some columns, adding tags such as PII, so people can kind of explore and understand how this data is modeled. And that's it. So there's a framework, probably just easiest if you Google Dataform. We have some docs. I put some examples from the talk up on a repo if you want to check it out. And our website has a ton of information, and you can try out the the web IDE for free. It's pretty easy to get started. There's example projects. And yeah, you can play around with it yourself. Cool. I don't know if there's questions, or would we not do
quick
that?
question here. We're going to do questions at the end. I'm going to let this man do a question because he stuck his hand up. But we're going to do questions at the end just for the sake of the pizza. So there you go.
Sorry. The question is, how do you compare yourself to DBT?
Cool. Yes, love that question. If you're familiar with DBT, then this probably sounded very familiar. Here's a story. We actually built, so we started building Dataform, the web IDE, as a web IDE on top of DBT. That was where we started. We saw what DBT did. We loved it. We thought it was amazing. We actually worked quite closely with the founders there and the guys working on it. And we started building out the web IDE on top of it because we felt that without that, it was very hard to adopt as a tool chain for people who weren't comfortable with software engineering or writing Python. So that's where we started. After a few months, we realized that there were certain things we wanted to do. For example, we wanted compilation to always be under a second. That was like a hard requirement for us because it makes developing extremely difficult if you have to wait a minute for compilation to happen each time. So there's that and a few other design decisions in DBT that really stopped us building the experience we wanted to build. And as a result, we kind of forked. I'd say conceptually, the framework is very similar. It certainly helps you model your data and build that graph. The implementation is certainly very different and has ultimately allowed us to kind of build that developer experience that we wanted to. So there was certainly some regret having to fork away from a popular open source project, but we felt it was necessary.
Right. So, ladies and gentlemen, can we give a generous hand of applause to Lewis, please? Thank you.